Okay, so let's move on to question 8c. So the question says that CF4 is non-polar while CF3Cl is polar. So based on this, they ask you to explain. So it's very simple. You just need to go back to your lecture notes, page 32. You will see this flow chart. So this flow chart teaches you how to check if a molecule is polar or not. Very simple. Does the molecule have polar bonds? So in this case, ask yourself, what do you mean by a polar bond? So for example, a polar bond will be something like HCl. So we have delta plus and delta minus here because Cl is more electronegative than H. So for polar bonds, it will be polar as long as there is a difference in electronegativity of the two atoms. So it is easy to remember. So if there is a difference in electronegativity, which means delta plus and delta minus, we can draw this arrow pointing towards the more electronegative atom. This thing over here, we call it the dipole moment. Okay, what I'm going through is just a quick recap of how to determine whether a bond is polar or non-polar. Okay, it must be determined based on the electronegativity of the two atoms. Moving on from here, you need to use VSEPR theory to determine the shape of the molecule. So in this case, of course, in your answer, you need to mention what is the shape of your molecule. And finally, your molecule should most likely have many dipole moments, so you just need to check whether they cancel out each other. If they don't cancel out each other, then your molecule is polar. If they cancel out each other, then your molecule is non-polar. So based on this, I would like to go on to question 8c. Okay. So for question 8c, you notice CF4 and CF3Cl. Let's do the shape first. So the shape is easy to draw, okay, because C will be 4, fluorine will be 7, 7, 7, 7. So which means they are single bonds. That means you should come up with this diagram. Okay, you don't need to draw the diagram in your answer, but for the sake of understanding, I have drawn it here. And for CFF3, C is 4, F is 7, 7, 7. Chlorine is also 7. So actually all this will form single bonds with carbon, and that is how we got this. Okay, so based on this, we know that all of them will have 4 bond pair, 0 lone pair. So their shape should be tetrahedral, of course. Okay, and in this case, we know that all of them have polar bonds. Why is it so? Carbon and fluorine. Fluorine is more electronegative, so dipole moment point towards fluorine. And also the same thing for the other bond. Then for CF3Cl, same thing. C versus F, dipole moment will be towards F because F is more electronegative. And of course, Cl is more electronegative than carbon, so dipole moment also point towards chlorine. Okay, and similarly for fluorine and fluorine. So in this case, all of these bonds, they are pushed to the corners, okay, of a regular tetrahedron. So you can imagine they are all at equal angles from each other. Of course, we know it's 109.5. So in this case, you notice that for CF4, so you know for CF4, because all the bonds are CF bonds, so of course the dipole moment should cancel. The dipole moment should exactly cancel out each other. So in this case, CF, it has no net dipole moment, and hence CF4 is non-polar. Okay, but if you go on from here, for CF3Cl, I actually have 3 CF bonds, and I have 1 CCl bond. So of course, the dipole moments associated with the polar bonds, they do not cancel out each other exactly. Okay, so based on this, CF3Cl has a net dipole moment, and hence CF3Cl is polar. Jot down your queries. If you're not sure of anything, on Monday we can discuss again. Moving on from here, let's take a look at question 8D. For question 8D, it should be more straightforward because the question talks about bond angle in NH3 is 107, but then in pH3 it is 94. So if you think of what you've learned before, bond angle, all these comes under a theory. What is that? The VSEPR theory. Correct? So that means in this case, in your entire answer, you need to explain the VSEPR theory in the format. Okay, the format that you always write it out. And then from there, you will need to explain why there is this difference. So of course, firstly, let's take a look at the molecule. I'm sure all of you should be able to come up with these two diagrams on your own. Not required in your answer, these two, but for visualization, I will show it here. So in this case, your nitrogen is 5, then hydrogen is 1, 1, 1. So this one should be single bond, and in this case, 1 lone pair left over. Similarly for phosphorus, 1 lone pair left over. That's why in this case, we have 4 electron regions around. Please, you need to specify around the N and P atom. Okay, 4 electron regions, so you have 3 bond pairs and 1 lone pair. And to minimize repulsion, the 4 electron pairs are directed towards the corners of a regular tetrahedron. Okay, regular tetrahedron. So as the repulsion between lone pair bond pair, okay, is more than bond pair, so both bond angles are compressed to less than 109.5. Take note that in this case we only have 1 lone pair, so we don't need to talk about lone pair repulsion. Okay, but in this case, how do we explain the difference in the bond angles? If you go back to your lecture notes, right, you will notice we will need to talk about this point known as the electronegativity. So for P, it is less electronegative than nitrogen. Okay, because if you look at the periodic table, nitrogen is above phosphorus, and we know that electronegativity down the group actually decreases. So P should be less electronegative than N. And because P is less electronegative than N, in your own thinking process, that means P has a lower ability to attract electron to itself in a covalent bond. So due to this, you will notice that the bond pairs will be, okay, wait now, in this case you have to include repeat. So based on this, please take note of the change in your answer. Because P has a lower ability to attract electrons to itself in a covalent bond, in this case, this part you need to insert electrons in the bond pairs are much further from P nucleus, from the phosphorus nucleus, compared to the electrons in the bond pairs from the N nucleus. What it means is simply just this, your P. So since the electrons are less attracted to the phosphorus, I can use this portion. Okay, you notice that the electrons are further away from P, whereas for NH3, because it has a higher electronegativity, it will attract electrons to itself more. They are closer. Okay, so very clearly you notice that because the electrons in the bond pairs are further away from P, the bond pair repulsion in pH3 will be smaller than that in ammonia. So in this case, the repulsion is smaller, just means that bond pairs are closer together. Okay, bond pairs are closer together. That is why the bond angle in pH3 is smaller than that in NH3. Okay, take a bit of time to digest this question. If you have any queries, again, we will talk about it on Monday. So as a summary, you notice this question, again, revisit, they are talking about bond angle, so we need to talk about the VSEPR theory first. So after we talk about VSEPR theory, we bring in another point, the electronegativity, to further explain why there is a difference in the bond angle.